Right now, tech companies are pouring hundreds of billions of dollars into facilities exactly like this. The market assumption driving this spending spree is straightforward. Investors believe that whoever builds the largest, most centralized, general-purpose model will secure a permanent monopoly over the future of computing. But beneath that financial enthusiasm lies a rigid technical reality. Artificial intelligence is still in its infancy, effectively a version 1.2 evolution. These models are notoriously inflexible, slow to adapt, and require staggering amounts of energy to process basic information. Building permanent, multi-billion-dollar physical infrastructure around an experimental, first-generation technology introduces a catastrophic level of financial risk. This dynamic is known as the first-generation trap. Companies lock massive amounts of capital into early, inflexible structures right before a major architectural leap in efficiency renders them obsolete. If a sudden algorithmic breakthrough arrives, it could drastically reduce the computational power needed to train and run these systems. Today's enormous data centers could instantly lose their value. It would be the equivalent of spending a fortune to build a colossal, state-of-the-art factory exclusively for 5.25-inch floppy disks, right as the CD-ROM was being invented. The underlying mathematics of artificial intelligence represent a genuine leap forward. But the financial ecosystem constructed around these giant centralized models shows all the symptoms of a fragile infrastructure bubble. In deeply competitive environments, raw scale eventually loses out to long-term efficiency. The entire history of computing proves this. The industry started with massive, centralized mainframes that consumed entire rooms. Over time, those monoliths were consistently replaced by smaller, decentralized client-server networks. Centralized systems inevitably accumulate heavy internal dependencies. And as they grow more complex, modifying, updating, or evolving them becomes prohibitively expensive. Legacy tech giants who dominated the early internet frequently tried to use their physical infrastructure and capital to delay this shift. They almost always failed. They were routinely defeated by competitors who deployed more effective, scalable algorithms, rather than simply throwing brute force hardware at the problem. Biological organisms and digital systems obey the exact same law. The architectures that adapt with the least friction, rather than the ones with the largest footprint, are the ones that survive. When we apply this historical law of decentralization to today's giant language models, their architectural limits become obvious. Looking at this technology stack, artificial intelligence currently sits isolated at the very top. It is entirely dependent on a long chain of intermediation. To execute even a simple request, the system burns massive amounts of energy and time just to punch data up through the operating system, the programming languages, and the applications. The second generation of AI will likely collapse this entire chain. Instead of software sitting on top of an OS, we are moving toward new processing architectures, where the intelligence layer operates directly at the hardware level. By designing silicon specifically for the tensor operations these models require, the need for a traditional operating system as an intermediary disappears. Stripping away these bloated software layers will drastically reduce the computational cost of running a model. When that happens, the main advantage of today's massive data centers gets neutralized. There is one final bottleneck holding back the current generation. To learn new facts or modify their behavior, massive models require full system retraining, a process that costs millions of dollars. Future models will solve this using structures known as translator tensors. These interoperable mechanisms allow specialized models to convert raw information into standardized code and instantly trade it. As small, hyper-specialized models trade tensors, they learn in real time, updating independently and eliminating the need for a central server. In this next generation, a model's value won't come from how much total data it hoards. It will come from how efficiently it translates and transmits specialized knowledge to the rest of the ecosystem. During the dot-com crash, many early internet companies vanished, but the underlying technology eventually integrated into every aspect of global trade and communication. Artificial intelligence will follow a similar path, even if many of today's first-generation giants collapse under the weight of their own infrastructure. The ultimate future of this technology will not be housed in remote data centers. It will operate as a living, decentralized network spread across billions of personal devices. In this state, intelligence is not contained in any single node. It emerges dynamically from the continuous interaction and collaboration of the entire network. This transition shifts the focus from building a single, all-knowing brain to cultivating a diverse ecosystem of specialized intelligences that can learn, evolve, and cooperate.